Good morning, good afternoon, or good evening, wherever you are. My name is Jan de Geer. I'm the director of Matrix, and welcome to this Matrix Online seminar. Today, we're very pleased to have Professor Andrew Hassell from the ANU, our newest ASC laureate professor, talk to us about mathematical breakthroughs in wave propagation. Just a point of order, if you have questions, we can invite you into the webinar. So please type in your questions using the Q&A function at the bottom of your screen, or just a few keywords, and then we can invite you in during the lecture. So at any time, just type in a question and we can invite you in and you can ask the question in person. So without much further ado, I want to hand over to Zhujia Wang, who will introduce Professor Hassell.
Hello, good morning, everyone. I'm Zhujia Wang. I'm Andrew Hassell's colleague at the ANU. Andrew is a professor and associate director of research in the Mathematical Science Institute at ANU. Andrew obtained his PhD from MIT in 1994. He was then a postdoctor at Stanford University. He moved to ANU in 1996 and studied at ANU. Since then, Andrew won the ARC Postdoctoral Fellowship, ARC Research Fellowship, ARC Future Research Fellowship. And most recently, he was awarded the ARC Laureate Fellowship. Andrew also won the medal of the Australian Mathematics Society in 2003, and he was elected to the Australian Academy of Science in 2013. Andrew's research involves different areas in analysis and PDEs, such as spectral and scattering theory, micro-local analysis, and semi-classical analysis, and many different areas of PDEs. The title of his talk today is Mathematical Breakthroughs in Wave Propagation. So let's welcome. So Andrew, you can go ahead.
Thank you. All right, I'll just share my screen here. Okay, so hopefully my first slide is showing. This is the title slide. Thank you for the invitation to speak. That's a great honor. So I was, as I understand, asked to speak essentially because I've just recently been awarded a Laureate Fellowship. The title of this fellowship, suitably immodest, is mathematical breakthroughs in wave propagation. And I'll just spend 2 minutes talking about the proposal. It comprises 3 interrelated research themes. So the first is nonlinear waves. And that's actually what my seminar will be on today. So that's global solutions of the nonlinear Schrodinger equation and introducing completely new methods, hopefully more powerful methods to solve these equations. The second aspect is rough waves. And this is about wave propagation in rough media. So essentially the problem or the issue is that we only understand wave propagation, which I'll actually define in a minute, when the media has roughly 2 derivatives. And when it has fewer derivatives, we actually don't really know when wave propagation breaks down. So when we can have a useful concept of wave propagation or when we cannot. So this is the second project, and that will be a real kind of fusion of harmonic and microlocal analysis. And the third topic is chaotic waves, and that concerns wave motion where we have chaotic related to a chaotic dynamical system. And so the if you like, the canonical example of that is the geodesic flow on compact hyperbolic surfaces. So this is a project on eigenfunctions on compact hyperbolic surfaces. But it would be futile to try to discuss all of these things in one seminar. So I'll just be concentrating on project A. But maybe I should actually say something in 5 minutes or so about what is wave propagation. What do we mean by that term? So let's take a simple wave equation, and this one, for illustrative purposes, will be the time-dependent Schrödinger equation. So that looks like this. So my capital DT is minus I partial derivative in t. That's a convenient normalization in Fourier analysis. And the Laplacian is this. It's actually the opposite sign, perhaps, to the usual one, but never mind. We can find wave packet solutions that are localized and oscillatory. So a wave packet looks like this. It's an oscillation, for example, a pure oscillation multiplied by a cutoff or an envelope so that it only has maybe compact support or is rapidly decaying. Okay, but it's assumed that there are sufficiently many oscillations that there's a well-defined frequency of oscillation in this region where the wave packet has support. So if we look at this equation, well, it's a simple constant coefficient equation, so you can find pure oscillations. So this factor here is a pure oscillation that exactly solves the equation, but because it's a pure oscillation, it's totally delocalized. So it's a bit hard to see what's going on. So what happens if we multiply it by a cutoff function to make it support in a small region? Well, then what we find is that this wave packet moves in a certain direction at a certain velocity. And it turns out that if you have this oscillation, okay, so the spatial frequency here is psi, then the wave packet will move with velocity 2 psi. So that's an approximate solution. It's not an exact solution, and you can't write down exact solutions like this in closed form, but it is the leading term in an asymptotic expansion in the parameter 1 over psi. Oops. So expansion in 1 over psi. So it's a high frequency limiting phenomenon. And it's quite a nice exercise, in fact, to apply this operator to this expression and see why we must have this frequency to get a good approximation. So as t varies, this gives us a curve of points in phase space. So we have t is the time, x is the position where this wave packet is centered at time t, and we have the spatial frequency psi and the temporal frequency, which I'll call tau, which in this case is minus length of psi squared. And it turns out that this point, xt psi tau, which is in phase space, or if you like, the cotangent bundle of Rn plus 1, moves according to a Hamiltonian dynamical system. And what's the Hamiltonian? It's the symbol of the operator. So our operator, which remember was capital DT plus Laplacian, has symbol tau plus psi squared. So we treat that as a Hamiltonian. The Hamilton's equations we can easily work out are these. So we see here the motion of the wave packet. These frequencies are fixed because it's constant coefficient. And that's what we mean by wave propagation. So wave packets, which are little things with small spatial support, but with a well-defined frequency of oscillation, move in a certain well-defined way, according to a Hamiltonian dynamical system. And so the mathematical technique I use most commonly is microlocal analysis. Microlocal analysis is analysis that takes place on phase space. In effect, we're tracking these little wave packets, and we can decompose functions into wave packets and see how they move. So in this way, we can actually decompose functions in phase space. And that's somehow the essence of microlocal analysis. All right, so project A, which I'm talking about, is on the time-dependent Schrödinger equation, or the nonlinear Schrödinger equation. But let's start with, so the nonlinear Schrödinger equation is this equation here. So this is exactly what we saw before. It's the time-dependent constant coefficient Schrödinger equation. then we'll have a potential function, which I will assume for simplicity is compactly supported in space-time. And now, of course, it's no longer constant coefficient. And finally, there's a nonlinear term, which there can be many nonlinear terms of interest, but the one I'm looking at is for some odd integer p, it's a constant times the norm of u to the p minus 1 times u. And this, by the way, this is a polynomial when p is odd in u and its complex conjugate. One can look at more general nonlinearities, but the ones that come up in physics and so on tend to be polynomial nonlinearities. Yeah, and this constant c could be positive or negative, and there are two different cases with different phenomena. So this models, yes, I see I forgot to say some of the basic things here. So we're working in Rn plus 1, where x in Rn is a spatial variable and t is time. This equation models, for example, quantum wave functions, and it also models, it's been used to model, for example, pulses in optical fibers in the case of x in one dimension.
So Andrew, there's a question in the audience by Kaylin. Kaylin, should be allowed to talk?
Yes, please. Kaylin, you're muted.
Yeah.
I'm afraid I can't hear anything.
No.
Maybe it's written down.
Kaylin, you need to unmute. Okay, the question, he's struggling with the microphone, but the question is, with the conditions on the potential V, could we represent something like the hydrogen atom with this potential?
Yeah, so not at this stage. So this is, the assumption on V is not very physically relevant, to be quite honest. Yeah, so for a hydrogen atom, V would be something like 1 over or minus 1 over mod x. And so that's time independent. It doesn't decay as time goes to infinity because it's constant in time. And it also has the blow up at the origin. So there's a couple of reasons why that doesn't fit. But this is a convenient assumption to make for beginning investigations. We are going to have more realistic assumptions on our potential as this goes forward.
All right. Okay. Yeah. Thanks for the question, Kaylin. Yeah.
Yeah. Thank you for that. And happy to field more questions as well. All right. So what should we ask about this equation? Well, the first thing that we can do is look for some simple solutions and see what the behavior is like. So of course we can go back to the these two terms. So V equals 0 means we're back to constant coefficient, and we can also set C equals 0. That gets rid of the nonlinearity. Then we're just back to the equation we had before. And of course, we can solve that with the Fourier transform. So this is easy. So with this equation, we find all the pure oscillations that satisfy that equation, which is just what I wrote down before. And then we now, because it's a linear equation, we can just superpose them with an arbitrary f. But now let's take f to be a very nice function, for example, a Schwartz function. Then what can we say about this u of xt? Well, we can say something about structure as x and, well, as t, for example, goes to infinity. So the phase here is a nice quadratic phase function. Provided t is not 0, it has non-degenerate Hessian, we can apply the stationary phase lemma. And that gives us some nice expansions for large t. So applying stationary phase, we get this expansion here. We get a power of t. So we're getting decay like t to the minus n over 2. We're getting an oscillation, which is, notice, a universal oscillation, doesn't depend on f at all. So we get this oscillatory term, and then we finally, f comes about, we get f of x over 2t. So x over 2t is the stationary point in this integral, in the psi variable. So that's very nice. But of course, that's very simple. We threw away all the difficult terms. What happens if we at least keep the potential, arbitrary potential, but we're still linear? So there's no nonlinearity yet. Well, it turns out, this is far from obvious, but it turns out that we get similar expansions, but now we get different coefficients. So we get an F minus. So these terms are the same. Factors. The first two factors are the same. And then the last factor, we get an F minus and an F plus. So we're getting different coefficients, if you like. So these coefficients, F plus or minus, are sometimes called the incoming data and outgoing data. Incoming is, if you like, coming in from minus infinity. The outgoing is going out to plus infinity. And they're also called radiation patterns. So this type of behavior is characteristic of linear solutions to Schrödinger equation and is referred to as radiation. So here's a bit of a picture. I don't know if I can get, yes, I can. Yeah, so here's a picture of these solutions, and the form of these solutions, actually, let me just go back to them for a minute. The form of these solutions really suggests looking at a compactification of space-time. And why is that? It's because x over t is a coordinate on the sphere at infinity. So here's a picture of Rn plus 1. This is meant to be Rn plus 1 compactified radially. So on each hemisphere, x over t is a coordinate. Okay, it's something homogeneous of degree 0, so therefore it's a coordinate on the sphere. And we can think of it as on the sphere at infinity. So that makes good sense on the radial compactification. What else did we have? We had a factor t to the minus n over 2. Well, that is just some function which decays at the rate of n over 2 at infinity, except perhaps at the equator where something more interesting is going on. And the oscillatory term, what does that look like? Well, x squared over 4t is a homogeneous of degree 1. And so this is actually a linear oscillation. It's a bit misleading. It looks quadratic, but when we're sending both x and t simultaneously to infinity. So this is homogeneous of degree 1, and it has a well-defined frequency at each point on the sphere at infinity. In fact, the frequency is exactly x over 2t, which we just get by differentiating in x. So linear solutions have that characteristic, this radiative character at space-time infinity. What about the nonlinear equation? What difference does the nonlinearity make? Well, in the case of focusing, which was the sign c less than 0, so maybe I should remind you of the equation. So this is capital DT plus Laplace in plus V u equals minus c u to the p minus 1 u. So in the focusing case, okay, sorry, I have it written there, I didn't need to do that. There are so-called Soloton solutions, and these look totally different. A soliton is a solitary wave, or a wave that does not disperse for a long time. And to see that you can get such solutions, we look for a T-harmonic solution. So let's prescribe our solution, or seek solutions of this form. So a pure oscillation in T times a function only of x. Well, this variable separates because the capital DT gives us an E. And then we just get an equation in a function of space. So now time has disappeared. This is a nonlinear elliptic equation, and for C negative, we can solve this equation, and we find there are solutions which are localized in the sense that the Q will be something like a bump with an exponential decay. And because of the form of the solution, it's not dispersing. As T, it maintains its shape for all time. So given that, we can ask some questions, and I've jokingly called it homework, but this is probably more like Fields Medal level questions, some of them. So question 1, do solutions of nonlinear Schrodinger look like radiation as t goes to plus and minus infinity? We've already answered that. The answer is no, because there are solitons which look different. So we can ask when, or are there any cases where solutions of nonlinear Schrodinger look like radiation? And in fact, there are. Small data solutions will still look like radiation, as it turns out. Question 2, what sort of soliton behavior can arise? So we just gave one example, but how many different solitons are there? Can you have solitons together with radiation? Can you have multiple solitons with radiation? And so on. All those sort of questions. Question 3, which is a general question related to scattering theory, is how do you relate the behavior or the asymptotics as t goes to minus infinity with the behavior as t goes to plus infinity? And question 4, are there some completely different behaviors which are unrelated to either radiation or solitons? Maybe there's some completely different looking solutions that we have no idea about. So there is something called the Soloton resolution conjecture, which says no to question 4. It's just a conjecture. We don't know the answer, but the conjecture is that actually at least the generic solution will break up into radiation and some separated solitons. That's a really hard question and a really interesting one. And it's the sort of question that's motivating this project and that I hope to shed some light on. All right, so we do have some preliminary results. Yeah, let me say that this talk is perhaps unusual because I've been more or less asked to look ahead and sort of say what might happen in this Laureate Fellowship project. So part of this will be kind of conjecturing or saying what we may be able to prove, but let's start with what we can already do. So I've been working with Jesse Gell-Redman and Sean Gomes, and earlier with Jacob Shapiro and Junyong Zhang on these sort of problems. And we have some results. So the first one is just on the linear Schrödinger equation, so no nonlinear term. And it's phrased in terms of this space WK. So WK is a Hilbert space, and the index K is measuring simultaneously smoothness and decay at infinity. So if you like, just leave it at that, but here is the definition. So we can apply, so WK is functions of F so that we can apply up to K operators to F, and we remain in L2, and the operators are all of this form. So I'm not sure how clear that is actually. These are commas here. Make them bigger. So these operators are either, so F is a function of psi here. They're simple operators, either multiplication by a coordinate function, a differentiation, or an infinitesimal rotation. And this theorem tells us that we can solve what's called the final state problem. So the final state problem is to solve the equation P equals 0. So P is the partial differential operator. Here the P is dt plus n plus v. So we're looking for global solutions to P equals 0 with prescribed asymptotic, which is of this radiative form. So exactly the form we saw before. So we prescribe F. So it's not the initial value problem where we prescribe something at t equals 0. Here we're prescribing something at t equals minus infinity, if you like. And so this says that if F is in WK, then we can solve we can globally solve the solution with prescribed radiative asymptotic, and it's also radiative as t goes to plus infinity, and the outgoing data F plus that we get so that's the radiation pattern at t goes to plus infinity, is also in this WK. So that, if you like, is saying the scattering operator, which is the thing that maps f at minus infinity to f plus at plus infinity, is a bounded operator on these WK spaces. Incidentally, we proved a bit more. We can actually solve the equation for f in WK for any integer k, even negative. And so we have this family of spaces. For k negative, these things are bigger than L2. And as we, in the limit as k negative, we get all temp distributions. So actually f can be any temp distribution. But only when k is at least 2 can we really write down this expansion. And we have a nonlinear result as well. So the nonlinear, so this is about the nonlinear Schrodinger equation, but it's a small data result. So that's a relatively, I mean, it's a early days, let's say. Small data results, it's the first thing you try to do when you look at a nonlinear equation, but it's just a first step. So now we have a condition on P and N. Remember P, the nonlinearity is an order P nonlinearity. It's like U to the P. N is the spatial dimension. So we have this condition. Now K needs to be larger than this. F is in WK as before, so that's the incoming data or the incoming radiation pattern, and we need it to be small. Then we can solve the final state problem for the nonlinear Schrodinger equation with this nonlinearity. And we can actually have either sign, so it doesn't matter whether it's focusing or defocusing. And moreover, U looks like radiation. So it has a radiative expansion as T goes to plus infinity, and the outgoing data is still in WK. So we still get this mapping nonlinear now, nonlinear scattering mapping from WK to itself. Yeah. So this doesn't contradict Soloton, the Soloton behavior, because of the small data condition. Okay, for the focusing equation, if we had large data, this wouldn't, a statement like this presumably wouldn't hold because solitons can form. But for small data, they can't form. I might just pause to see if there are any more questions that have shown up. Okay. So now, as I mentioned before, the point of this Laureate Fellowship is to introduce a completely new method to solve nonlinear Schrodinger equations, and by the way, other nonlinear wave equations that should have some general applicability. What's the conventional approach? The conventional approach to solving NLS is to view it as an evolution equation in time and to specify an initial condition at time 0. Okay, so given a initial U0 of X, we solve the equation. And that makes good sense because it's a first order equation in time. And then to analyze the sort of problems I'm talking about, the long time behavior and scattering, this is analyzed in a series of steps. So the first step is to establish local well-placedness. So given the solution at time 0, we want to solve it in a possibly small time slice. And the next step is to show global well-placedness, to actually show that this time slice is the whole real line and not just a bounded interval. By the way, some nonlinear Schrodinger equations will blow up. So, I mean, it's not necessarily the case that you can show global well-placedness for all equations. And then finally, scattering. So then you additionally have to show that as t goes to infinity, this solution that you have converges to a linear solution, some other solution to the linear equation. Now, in this new approach, which I've mentioned some of the people, Jesse L. Redman, Sean Gomes, Jacob Shapiro, Junun Zhang, it's based on prior work, especially from Andras Vashi, but also Peter Hintz, Andras Vashi, and Dean Baskin, Jared Wunsch, and Andras Vashi. we're going to view the operator globally. So we want to view it as an operator on functions on the whole of space-time Rn plus 1. So our function spaces will be functions defined on all of space-time.
Andrew, we have a question from Zhang. Zhang, if you would like to enable your microphone and camera, you can ask your question.
Okay, and hi, Andrew. Yeah.
Hello.
You said that if the initial data is small enough, so we can only get the radiation solution. If the initial data is larger, it maybe produce some Soloton solution. Yeah.
Yes.
So, is there any threshold for the how large the initial data will be?
Well, yes, I expect so. I mean, so there is something known about this by work of people like Nakanishi and so on, and others who have looked at thresholds. We're not quite at that stage yet, so I can't say more than what is already known from other work. But yes, I expect that there will be a threshold. So, for example, yeah, there should be there should be a threshold in terms of, say, the WK norm for a soliton to emerge. But I think there are more kind of invariant quantities associated with solitons that we can identify to say, below this level, we can't get solitons, and above it, we have solitons. So, you know, there are various results to say the ground state soliton is kind of the first thing that can happen. So below that, in whatever below means, we only have radiation.
Okay. Okay. Thank you.
Yes, thank you, Junyong, for that question. Yeah, so our function space is defined on all of space-time. And what we look for is some natural Hilbert spaces so that our operator P, so remember P is the linear part, the linear operator in the nonlinear Schrodinger equation. This P is invertible between these spaces. The invertibility is a really powerful property, and it hasn't been available in the standard approach. So the more common, so of course, once you have invertibility, then we have an inverse map, which maps in the opposite direction. And I would say currently in the literature, we have P inverse we know is bounded from various spaces to various other spaces, but we don't have P mapping boundedly in the other direction. So we only have it in one way. So to have the two-way invertibility, I think, is going to be very powerful. And we're going to get two inverses. So what are these plus and minuses? The plus and minus really indicates the advanced or retarded inverse. So if you think in terms of time evolution, if you imagine solving PU equals F, where F is localized in space-time, maybe F is supported between t equals 0 and t equals 1. Well, then there'll be we can solve the equation forwards in time, and then the solution will be supported for t bigger than 0. But this equation is time reversible, so we can solve it backwards in time, and that solution would be supported for t less than 1. So we expect to find these two inverses. And what are these spaces? X plus or minus and Y plus or minus. Well, this gets a little technical, and I don't want to give a technical talk here. So I will say just some brief words about it, just to indicate that, I mean, as spaces, these are not some sort of trivial. Of course, one could do this in a trivial way, which would be useless. And this is not that. This is really giving some powerful information here. So these spaces are based on weighted Sobolev spaces. I put parabolic in there. So we work in a parabolic calculus that's adapted to our operator, which is parabolic in the sense that it's only first order in time and second order in space. But we work in a calculus where dt is actually a second order operator. So that's what parabolic means. Weighted Sobolev space. So weighted Sobolev space, we have two indices. S is the regularity or smoothness index. S is how many derivatives we have in L2. And R tells you how much decay there is at space-time infinity. Is it decaying faster than L2 or is it growing? Yeah, but there are some subtleties, and the main subtlety is that R actually needs to be a variable space-time decay order. And what's worse is that it varies in phase space. So actually in different regions in phase space, we need R to have different values. So just to go back to so this is really intimately related to these radiative expansions. Maybe I'll just go back to that picture that I had before. Sorry, I've got to flick back through a few slides. Yeah. So remember, we observed that this sort of typical oscillation that we get in these radiative expansions has at each point on the sphere of infinity indexed by x over t, we have a frequency, which is x over 2t. And so there's a well-defined region of phase space that's associated to these sort of expansions, and these are called radial sets. And we're building into the space, actually, the expectation that we have these sort of expansions. So that's one feature of these spaces. And what we do is we choose weights so that in the space with a given weight, so these are called R plus and minus, say R plus will allow these sort of expansions. So functions in our space can have these sort of expansions as t goes to plus and minus infinity. Sorry, as t goes to plus infinity, but not as t goes to minus infinity. So we can only have one of those two expansions. And the other weight, R minus, is the reverse. R minus will allow this expansion as t goes to minus infinity, but not t goes to plus infinity. And, okay, so that's obviously a bit vague. And what does it even mean to have a space-time decay order that depends on the frequency variable? Well, I'm not going to say, but you need pseudo-differential operators, and you can define these things. So then y plus is a space that looks like this, and x plus, well, it's not quite HSR plus, but we also have this condition. So it's like a domain space. It's like we start here, and we want to end here. So our domain is a set of functions for which that's true. Yeah. So you will notice that with this definition that it's a triviality to show that P is a bounded operator from x plus to y plus, because we've built that into the space. But what's highly non-trivial is that it's invertible. That's a really powerful statement. Yeah, so there's an analogy with functions associated with the Laplacian on the unit disk. So the analogy is as follows. So let's look at the Laplacian on the unit disk. That's the most classical PDE you could possibly imagine. And you might ask, can we find two Hilbert spaces between which the Laplacian acts invertibly? And the answer is yes. We can take, well, we can map it into L2 of the disk. D will be my disk. And we'd start where we need spaces, functions with two derivatives in L2, so that'd be H2. But H2D doesn't work. We have H2D intersect H10 of D. So this 0 means we're imposing the Dirichlet boundary condition. So with the Laplacian, we have two pieces of Cauchy data, the function on the boundary of the disk and its normal derivative. And what we need to do is to kill one of those pieces of boundary data. So in other words, the function space has to impose that, say, the Dirichlet data is 0, which is just what this is doing. And then we get an invertible map. So the Laplacian is indeed an invertible map from here to here. So we have two pieces of Cauchy data, we have to kill one, and then we get this invertibility. And it's very much the same here. These spaces x plus and minus, the r plus and minus are chosen to kill one of the pieces of boundary data or these radiation patterns. So they're like the Cauchy data. If we kill one of them, then we get invertibility. Yeah, and how's invertibility proved? Well, I'll say not very much at all about this, but just for a minute or two, what we do is we prove what is called a Fredholm estimate. So the Fredholm estimate is, if you like, the opposite is what we need. So as I said, P will be a bounded map from here to here that's built in. So we need the opposite inequality, which is that PU is bounded above by this. So we need this inequality. And ideally, we just prove this without this term, but analysis is a messy subject and we always have error terms. So we prove the estimate with, and we need to have a weak norm of U on the right-hand side. So M and N, let's say, are very large. So this is a very negative order Sobolev space, and that's a very weak norm. So if we can prove this for R plus and the similar estimate for R minus, then there's a totally abstract functional analysis argument that shows that P is a Fredholm operator from x plus or minus to y plus or minus. And then Fredholmness is almost invertibility. So Fredholm operator is one which has closed range, and both its kernel, its null space, and its co-kernel are finite dimensional. So it's only finite dimensional. It's only finite dimensions away from being invertible. You can show invertibility actually using mass conservation of the operator. That's just a slight additional argument. But in some more elaborate settings that we'll come to, invertibility may not hold. And these finite dimensional kernels and co-kernels may hold key geometric or analytic information. So I'm just looking at time here. Yeah, I think I'm going okay. So let's just briefly outline how, using this new method, we can solve the final state problem. The final state problem, remember, just for the linear equation, say. So the linear equation is PU equals 0. We want to solve PU equals 0 with given incoming data F. So we have this radiative expansion as t goes to minus infinity, and F is the incoming data in that expansion. And actually, it's kind of straightforward with this framework. So what you do is you first solve so P is dt plus n plus V. So let's ignore the V for the moment and just look at this constant coefficient equation, which is easy to solve with Fourier analysis. So given the F, we use Fourier analysis to find U0. And this, by the way, I'll call this operator P0. The P0 is when V equals 0. So using Fourier analysis, we easily find U0. And it turns out to lie in x plus plus x minus. You know, it has expansions both as t goes to minus infinity as t and as t goes to plus infinity. So it can't be in either space alone, because as we said before, functions here only have expansions as t goes to plus infinity. This only has the expansion as t goes to minus infinity, but it does lie in the sum. Not only does it lie in the sum, but there's a natural way using microlocal analysis to divide U into a piece, U minus, which is an x minus, and U plus, which is an x plus. And so U minus alone has the prescribed asymptotics, the ones we want. Because U plus doesn't have an expansion as t goes to minus infinity. So now I claim that P U minus is actually in Y plus. We know P U minus would be in Y minus because P is invertible from X minus to Y minus, but actually it's also in Y plus. So why is that? Well, we write PU minus as P applied to U0 minus U plus. So using this. Okay, and then that's P0 plus V. P is P0 plus V applied to U0. minus pu plus. Well, P0 of U0 is 0. We've solved that equation. So we just get VU0 minus PU plus. And now this is definitely in Y plus, because P maps from X plus to Y plus. What about this one? Well, U0, where is U0? U0 is in what are these spaces? H, S, plus H, S, minus. So U0 has more derivatives than we need. It has S derivatives, whereas Y only has S minus 1 derivatives. But it doesn't have as much decay as we need, because this is only R plus, which is not as good as R plus plus 1. But the V is compactly supported. So once you multiply by V, this has any amount of decay. So for that reason, we have more than enough decay and more than enough derivatives. So this is in Y plus. And once it's in Y plus, we can apply P plus inverse to it. So now we just let U to be U minus. So U is U minus P plus inverse of PU minus. And that's the solution. That's a global solution. So the key is to use the correct inverse here, because if we put P minus inverse here, P minus inverse would be an inverse to P on X minus. So P minus, that term would just be U minus. Then we'd get U minus minus U minus. Sorry. Yeah, then we'd get U minus minus U minus. So we just get the zero solution. So that's not interesting. But with P plus inverse, what do we get? Well, this has the correct asymptotics as t goes to minus infinity. And this has no asymptotics as t goes to minus infinity, because it's U plus. Sorry, because it's P plus inverse. So this is in X plus. Yeah, so we actually have a very direct way of solving the final state problem. We do not have to go through this process of local well posedness, global well posedness, scattering, and so on. It's a direct sort of method. And we actually use the mapping properties of P in both directions in this argument. So that's really exploiting the invertibility. Okay, so time's moving on. So let's look forward now to what we might be able to do in the future during this Laureate Fellowship. One thing is that we would like to do, for example, is look at solitons and solutions near solitons. So if you like, the nonlinear stability of solitons. So this has been investigated by people like Schlag, for example, but for one thing, I expect we get stronger results with this method. For another thing, this is a stepping stone towards working to multi-solitons and so on. Yeah, so what happens when we can first look at linear stability. So we linearize the equation about the soliton, and then the soliton is going to act as a potential function. Now, this potential function, the nature of the soliton, if we look at this basic soliton, what's called the ground state soliton that I mentioned before, is it's time independent, so it doesn't actually fit in our framework. We're going to need to extend the framework to deal with time independent potentials. And just a picture here. Yes, there's a picture. Okay, so this is, again, this is the compactification of Rn plus 1. And what I've drawn is the sphere infinity. The soliton, if it's stationary, is just lying along the t-axis, so along this dotted green line. And so there are two distinguished points at space-time infinity. So the soliton is not small at these 2 points. It doesn't decay. So we need a slightly different geometry. And it's actually a very similar to geometry to three-body geometry, of which a certain amount is known. So my student, my PhD student, Yilin Ma, is working on a Fredholm framework for a three-body problem, and then that will also apply here. So in this case, I expect the linearized problem to be Fredholm, but not invertible. We shouldn't have invertibility here. Why is that? Well, there are two phenomena that may destroy invertibility. And the first one is that if you think about the stability of the soliton, we can take the soliton and we can apply some radiation. We can add some radiation, and the radiation and the soliton will interact in something non-linearly, and something will happen. So even infinitesimally, so we linearize, there's some interaction, and we would expect the soliton to pick up a velocity. And so instead of being on this green trajectory here, it would it'd be an interaction, and then it would shift. Yeah, so implicit in here is the fact that you can apply Galilean transformations to solutions. So there's a symmetry group. So as well as having stationary solitons, you can have solitons moving with any fixed velocity. And so this would be perturbed from one velocity down here to a different velocity here. But notice that that means that the two distinguished points have moved. So maybe this one's fixed down here, but this distinguished point where the soliton reaches space-time infinity has moved. So what that means is that you wouldn't expect P, well, it's a bit of a vague statement because I haven't told you what these spaces are, of course. And in any case, we may have to, the initial guess may not be correct, but for our initial guess, we probably won't get surjectivity because the general perturbation, so that this X plus would be a fixed space, which corresponds to these 2 points being fixed. But the general perturbation will map this point to some other point. So the co-kernel of this map should basically encode the n-dimensional space of possible velocities that this soliton can pick up. So for that reason, I believe the Fredholm framework is going to be a very powerful framework for dealing with this. It's this problem and moving from to nonlinear stability or otherwise of the soliton. In fact, the soliton is not always stable. So Schlag has shown that in some cases, there are a finite number of unstable modes, and this may require a modification of our function space to have exponential weights in time, because we'll get exponential blow-up. So then you have a choice of weights, and you can choose a different weight as t goes to minus infinity and as t goes to plus infinity. And these weights will affect the index of this Fredholm operator, will affect the dimension of the kernel and co-kernel. It's time for me to stop, but actually I'm almost finished, so let's wrap up. So I guess where we're heading towards is just trying to solve a final state problem where we're given several solitons coming in from different directions and different velocities from t equals minus infinity plus radiation, and trying to solve that problem. And yeah, in view of time, I think I'll stop there. So thank you for your attention.
Thank you, Andrew. Are there any questions or more questions? Yes, someone raised hand, and you can ask. You can. I see a hand. Any questions?
I'll just allow Stephanie to talk. Or Stefan.
Stefan seems to be muted still.
Andrew, I may ask you a question. When you introduce the new approach, you introduce the new space HSR. For the R, it's the R, the sub R, super R is for time t, right?
So it's a space-time decay. So if you just think of R as being constant, so if R is 1, for example, then you have 1 order of additional decay. So if you like relative to L2, so it decays like maybe 1 over T times something in L2, or 1 over mod X times something in L2.
So does the decay is the same in the future or in the past and in past?
No, it's not. In particular, it's different. So there are 2 microlocal regions associated to the 2 expansions. So we have these 2 expansions. These microlocal regions are very significant, even geometrically. They're basically where all the trajectories start and finish.
Yeah.
And so R plus and minus, yeah, I didn't say, but there's a threshold value which happens to be -0.5, which has to be avoided. So we don't get Fredholm properties when R plus minus is -0.5 at these 2 sets. But what you find is actually it has to be bigger than -0.5 at one of them and less at the other one. There are 2 choices for that. So that gives you the plus and minus. And it also tells you that it can't be constant.
Yes.
Yeah.
So I learned later about Schrodinger equation. So for Schrodinger equation, how many different solitons can you classify all solitons?
Well, that's
for the linear case, for example.
In the
linear case.
Well, we don't get solitons in the linear case. So the solitons require the focusing term.
Okay,
yeah. The focusing term, by the way, acts like a negative potential. So a negative potential can, even in linear theory, can create bound states. And in the nonlinear case, it can create the solitons. They're bound within this region. Yeah, so they're an intrinsically nonlinear phenomenon, and so people have studied them. There are lots of results of kind of very specific natures. Like, for example, people have looked at initial data consisting of widely separated solitons that won't come close to each other and show that you can find a solution that looks like that.
Okay. So there are many solitons for nonlinear case.
So there's lots of examples, but we don't have general theory, as in we can't say the general solution in this class breaks up into solitons or is composed in some sense of solitons plus radiation as t goes to plus and minus infinity. So that's out of reach at the moment.
Shuja, we have a question from Jun Yong.
Yeah.
Hi.
Hello.
Yeah, in your cases, try to prove that nonlinear solutions. You assume that the potential V is decays faster enough. Yeah.
Yes.
So I want to know how fast it will be needed. Does it conclude the Coulomb potential or not?
Yeah, so one of my next projects will be with various collaborators to generalize V so that it doesn't have to be compactly supported in space-time. It will actually lie in one of these spaces. Well, okay, so we use slightly different spaces called module regularity spaces, but for the purposes of this talk, we can think of them as being like these spaces. So the V itself will lie in the, because what we want to do is to linearize about a particular solution. So the V will actually be a power of U.
Yeah.
And we know where U lies. We know the sort of function spaces where U lies, and we have some multiplication results. So we know where powers of U lie. So that they'll lie in some particular space that looks like this. And we want to treat V, the sort of V that lie in that space. Then that will become useful for doing linearizations in the nonlinear Schrodinger equation.
Okay.
Yeah. It turns out that we have to move, well, you know this, Junyong, but for other people, we have to move to slightly different spaces called module regularity spaces in order to have good multiplication properties. So really, we need multiplication because the nonlinearity is polynomial. And But once we have that, then V can be in those spaces themselves, because the V times U is a multiplication, and we'll have good results about where that lies and what function space that will lie.
Okay, yeah. So that means you need to establish the new the linear estimate, yeah, including the V, not only get rid of the V.
That's right. Yes.
Okay, and another question is a bit about the details. Here is the in the radial solutions here. The F is the incoming data. How does it connect with the initial data for the Schrödinger equations, just like the U0?
Yeah. So far we haven't kind of cared about what the initial data looks like. So we're actually not looking at time slices. We never need to. So we don't look at, but of course one can still ask the question, restrict U to a time slice, a particular time, what does it look like? Okay, so I know how to answer that, at least in the case of the constant coefficient equation. So the linear equation with no V. Then this F is just the Fourier transform of the initial data.
I have do some computations. The F looks like the Fourier transform of the initial data and convolution or another kernel. It's about, but I don't know how. Here you assume the F, the incoming data is small in the WK spaces, but I don't know how to put these assumptions on the initial data, or just like something.
I see. Yeah. So the WK, I guess, is its own Fourier transform, because it kind of has a its definition is invariant under taking the Fourier transform.
Okay. 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 Thank you. That's all.
Yeah.
Any more questions?
So did Stefan have a question? Did he?
I didn't see any questions. Okay. Then let's finish. Okay, Andrew, your talk very, very clear. Thank you for your great talk. Also, thanks to everyone who come to this talk. So that's all for today. Thank you.
Thank you very much.